So, good afternoon, everyone. So, this is the Week 9 NPTEL tutorial course for the course named as A Study Guide in Organic Retrosynthesis Problem Solving Approach. The course instructor for this course is Professor Samik Nanda from IIT Kharagpur and myself Anirban Maiti from IIT Bombay, one of the TA for this course. So, we'll move further to see in the retrosynthesis we have seen the syntones and synthetic equivalents we have discussed about. So what is syntones and synthetic equivalents, and we need to know about these terms because in retrosynthetic analysis this will help you a lot when you will perform any retrosynthetic analysis. So this will help you in your problem solving approach. So basically when symptoms and synthetic equivalence comes, okay. So if you have your so in if you break any carbon carbon bond, right? So let's say this red bond is carbon carbon single bond, right? Now if we break this cc bond, so what will happen? So this can this bond is having two electrons, right? So now each carbon can abstract each electron from this bond, right? So one electron they can share. Otherwise one of the carbon can abstract both electrons, or other way this carbon can abstract both electrons, right? So what will happen? So in first case, like if they share each electrons, then it will be homolytic cleavage, like the cleavage, the breaking is happening in homolytic fashion. But if one of the carbon atom takes two electrons from this bond, what will happen? So that will be the heterolytic cleavage, right? And in heterolytic cleavage, you will see the end up of a carbon negative charge and carbon positive charge, mean carbocation and carboanion, right? So this is very obvious. And this donor syntone, the term, if you see donor syntone, donor mean it can donate, right? So that means it should have electrons to donate. So that's why if you have this carbon and in this carbon atom, so that time we can call this as a donor syntone, whereas this carbon atom will bear positive charge or carbocation, so we can call it as acceptor syntone, right? So this donor syntone and acceptor syntone, so these are known terms. Now if you want to do the forward synthesis, okay, so let's say in retrosynthetic plan we can think about this cc1 disconnection and via heterolytic cleavage. Now if we break this cc1 via heterolytic cleavage, so we'll have this donor syntone and acceptor syntone. So these are not existing existing molecules, right? So we need to, for forward synthesis, so for our convenience we are breaking and we are getting these two fragments. One is carbocation and another is carbanion, but these two fragments really does not exist in real life. So in forward synthesis we s- like we can't start with these carbocations and carbanions. We need to use some neutral molecules, and in situ we can generate these carbocations and carbanions, and they will undergo reaction to give this cc1 formation product, right? Now so forward synthesis we need to use some equivalence of donor syntone or some equivalent of acceptor syntones, right? So that we need to know. So what will be the synthetic equivalent, okay, for particular donor syntone and for particular acceptor syntone? So this we need to know clearly, okay. So now let's say, so this is the donor syntone, okay. So now we'll talk about for donor syntone, okay. Then we'll talk about acceptor syntone, okay. So now this donor syntone, let's say alkyl anion. So this alkyl anion mean suppose methyl anion, okay, methyl carbanion. So this methyl carbanion, okay, so one carbon it is having. So how we can generate, suppose we need this methyl carbanion in the reaction, forward reaction. So how we can generate? So we can generate from Rx, okay, Rx mean methyl iodide, we can say. For methyl anion carbanion, we need to have methyl iodide, X mean halides, right, methyl iodide or bromide. And we need to convert this methyl iodide or bromide to methyl magnesium bromide or methyl magnesium iodide or methyl lithium. Okay, so we need to generate some organometallic pieces, so that this metal center will bear positive charge and this carbon center will bear negative charge. Okay, so we can generate this alkyl anion pieces. Okay, so very interesting. See, yeah, for cyanide ion, similarly for cyanide ion, suppose we need cyanide ion, okay, as a nucleophile. So suppose we want to do some SN2 reaction, okay. So this is halide, ethyl iodide, and we need to convert this ethyl iodide to cyanide, okay. So we need some nucleophilic source of cyanide, right? This is very obvious. So we need cyanide ion. So but cyanide ion is not exist in pure form, so we need to get some reagent. So from HCN we can generate NaCN, and this NaCN is the reagent, Na plus and Cn minus. So this is basically salt, Na plus and Cn minus. So it will exist in a ionic form or salt form, okay. So this cyanide can act as a so cyanide ion we can get from NaCN or potassium cyanide. Okay. Okay. Now let's say this RC triple one C minus. Okay. This mean acetylide anion, acetylide carbon ion. So from where we can get. So this is the neutral pieces RC triple one CH. Now we need to generate this acetylide anion. So here it is C minus and Li plus. Okay. So we can treat with butyl lithium. Okay, so butyl lithium is mm, base. So this will abstract proton from this acetylene proton, and it will give this acetylide anion. Okay, yeah. So similarly, what will happen to this enolate? If we want to do some enolate kind of chemistry or reaction, suppose in aldol reaction, okay, aldol reaction we need to do the enolate formation, right? So this enolate can attack another aldehyde, and it will give aldol product or beta hydroxy. So beta hydroxy ketone will give, right? So for enolate generation, how we can generate enolate? So we can start from normal ketone or carbonyl compound, and if we treat with LDA or some NaOH or some other bases. So here let O lithium enolate is there, so we need to treat with LDA. So, and we will get easily the lithium enolate, right? This is very simple. And the next example, if you see, this is elide, okay. So elide mean in case of Wittig reaction, okay, Wittig reaction we need some elide chemistry, okay. Elide mean, so the so next to like ppst plus, and then the next atom should bear the opposite charge, okay. So that time we will call as elide. Now so this elide is important in Wittig reaction, okay. So we need to generate elide in Wittig reaction, and how we can generate? So this is the secondary halide, okay. Hex means halogen, Cl bromide, iodide, okay. So if we treat this with pph3, that time we'll get this Wittig salt, okay. So this is ppsc plus x minus, so this is the Wittig salt. Now if we take proton, so this alpha proton next to ppsc, if we take this acidic proton by treating with potassium tertiary butoxide or n-butyl lithium strong base, that time we can generate the carbanion at this center, right? So that is called elide. Okay, very interesting. And this alpha nitrocarbanion, so from any nitro species, if we treat with base, this, so alpha to nitro protons are acidic. Okay, so base can easily take proton from alpha position of a nitro group, and it will give your corresponding alpha nitrocarbanion. Okay, very simple. So we have seen here some examples of donor syntone and where we can use these donor syntones and from where we can get the donor syntones. Okay, that means in the equivalents and derived reagents we have seen. Okay, so similarly for acceptor syntone, how we can think? Okay, acceptor syntone, if you see, yeah, this is the alkyl cation. Okay, alkyl cation mean, suppose here it is CH2 minus, so here it will be CH3 plus. Okay, so CH3 plus. Okay, so from where we can get, so we can add like the corresponding synthetic equivalent will be methyl iodide. Okay, because iodine is electronegative, or methyl chloride or methyl bromide. So this electronegative halide atom, if we have with attached to this carbon atom, so due to the electronegativity of halide, so this carbon can we easily generate positive charge. Okay. Similarly, this acylium anion, if we treat with, like from where we can get, so if we are having this rcox, okay, x mean chlorine or nme2 or ome, like that. Okay, now similarly this beta carbocation next to carbonyl, how we can generate, if we have this alpha beta unsaturated, so this is the alpha and this is beta position. Okay, so alpha carbon beta carbon, alpha beta unsaturated carbonyl compound, then this beta carbon is always positive charge. So if we need this beta positive charge, so we can think about this alpha beta carbonyl unsaturated carbonyl compound. Also this alpha carbocation next to carbonyl, so if we have alpha bromo or alpha halocarbonyl compound, we can easily generate this carbocation. Okay, very simple. Similarly this beta carbocation next to a hydroxy group, so we, if we have, so this is alpha, this is beta, if we have this beta, ketone, not ketone, epoxide, so then we can easily generate this beta carbocation next to hydroxy group. Okay, so I, so you have so so in this slide you can see how many like different types of synthetic equivalence come like with respect to the each donor syntone, and with respect to some acceptor syntone we have seen the synthetic equivalence, right? So this will be helpful in our retrosynthetic problem solving section, and it will also give you idea how these reactions works and what type of reagents we need when we will think about some donor symptoms, okay, or receptor symptom. Yeah, so if you have any doubt you can ask in this slide, or you can write in the comment section. Okay, so yeah, next slide. So we'll solve some retrosynthetic problems with with some molecules. So let's say we are having this aromatic ring containing this amine. One is aromatic amine and another is aliphatic amine. Two amines are there. So how we can plan for this molecule? Okay, like how we can design the retrosynthetic plan for this molecule. Okay, so you can think and you can draw in your own notebook. And let's say we are like when I will move forward, let's see whether you draw the correct one or not. Okay, so just draw in your notebook and think. I'll give some time. Like what will be the next arrow in the past retrosynthetic plan? Okay, so if you see this molecule, the functional groups presence in the molecule is amino group. Okay, one is this aromatic night amine and another is this aliphatic amine. Okay, but this is tertiary amine, right? Okay, in aliphatic, so you have to see that this is tertiary amine. So what can we do with this molecule? Some functional group interconversion we can do. FGI. So what is this FGI? Functional group interconversion. Like what type of functional group or FGI we did in this conversion? Okay, just tell me, or you can write in comment section as well. We can discuss in YouTube comment section or in this leave session also. You can ask me any doubt, or you can whenever I will ask, you can answer. Okay, freely you can ask. So what type of functional group interconversion in this fast arrow, fast retrosynthetic arrow? More, if you see, it is very much easy. So we are doing NH2 to nitro. Okay, that means in forward synthesis we have to do nitro to amine. So that is reduction of nitro, right? Very simple. Now what type of CC bond disconnection? Now I will give you an clue. So the next step will be the CC bond disconnection. One of the CC bond disconnection. Okay. Now if you see which CC bond disconnection will be more favorable. Okay, so you can think in your mind, and I will suggest you that this aromatic CC1 disconnection is impossible, right? Aromatic ring is highly stable, so you can't do it aromatic. Like you can't break this aromatic carbon carbon double bond or carbon carbon double bond. Okay, so what is the other possibility to move forward? Okay, so like which CC1 disconnection we can do? Think and tell me. So I told you ki this part you should remain intact. Okay, so now there is possibility. Okay, so this is the functional group. Okay, so nitro is electron withdrawing group. Okay, electron withdrawing group mean, so basically you can generate carbon ion at this alpha position easily. Okay, so you can think about this CC1 disconnection, and this CC and this CC both are same molecule. Okay, so this is methyl side chain are there. So one of the CC is okay. So symmetrical, or you can generate this CC. Okay, let's say this is one, this is two. Okay, which one is more preferable? Okay, both are preferable, but in first step, what will what we can do? Like if you are thinking about this one approach one, that time we will break this CC bond and we will have some electrophile here at this carbon, and nucleophile is we can easily generate nucleophile by treating with base with this fragment, right? And for second fragment, so we need to have methyl iodide as a electrophile electrophilic reagent, and this nitrogen, okay, this nitrogen, okay. So I guess this first one is more favorable because in this will be the symmetrical nitro, and that we can prepare easily. So like that, this first retrosynthetic arrow, we have got these electrophiles and this nucleophile. Okay, so this is isopropyl nitro group. Okay, so it is having one proton, so we can easily abstract proton from this nitro, and this will become nucleophile, and it can undergo nucleophilic substitution reaction. Okay, right. Yeah, so it will give this product. So now that is okay. So if we think about the retrosynthetic disconnection approach for this nitro group, again we can think about this CC1 disconnection, and this will give you this nitromethane. Similarly, okay, similar type of chemistry. Nitromethane you have to treat with base. This is the Me, okay, plus methyl iodide, okay, methyl halide, any base. So this, if we treat with base methyl nitromethane, so it will undergo carbonyl and it will undergo nucleophilic displacement to give this isopropyl nitro. Okay, very simple. So for our synthesis, we have to see what is happening. Yeah, any doubt in this slide, you can ask me, or you can write in the comment section. So in comment section also you can write and we can discuss. Okay, if you have any doubt, or in this leave session also you can ask freely. We can clear your doubts now itself. Okay, so this is the retrosynthesis. Now we will see the forward synthesis. Okay, so forward synthesis we will directly start from this isopropyl nitro. So like this. Okay, so the pK value of for this nitro compound, the acidity is around 910. Okay, 9 to 10. So we need some strong base. The pK value more than this 910. Sodium ethoxide, the pK is around 15 or 16. So these are the pK value. Okay. So pK value of base mean the conjugate acid of base is having pK value 15. Okay. That means the stronger base than this. Okay. So this sodium ethoxide, what it will do? It is base, and you are having some acidic proton. You need to find some acidic proton. Where is already I have mentioned here by using by showing the pK value. Okay, so you can guess what will happen. Yeah, so what will happen? Sodium ethoxide Na plus O80 minus, so it will abstract proton from this nitro, like alpha to this nitro group. Okay. So what will happen now? So it will generate this carbon and right. So now you have your nucleophile ready, and so nucleophile ready. So it with whom it will react. So you need some electrophiles around to it, so that it can react with electrophile. Okay, so what will be the electrophile here? So benzyl bromide. So like this nitro 4 nitro benzyl bromide is there. So now this benzylic position is electrophilic. Okay, and you have bromide your in your substrate. So what will happen? It will undergo this nucleophilic substitution as benzyl position. Okay, right. So what will be the product? Write down. Then I will show. Write down the product of this electrophilic substitution. And sorry, SN2 reaction. Okay, then I will write. I will show you. So have you write? Yeah, I'll show you. So this will be the product. Okay. So any doubt? This is pretty forward. Then now the next step. So now we are doing the reduction. Okay. So if you see the forward synthesis, we need to do some nitro to amine conversion. Okay. So this reduction we can do, and we got our compound, right? We got our final compound. So that is what we need. So this was our target molecule. So the next problem we will see, again we are having this nitro amines, amines compound. I have given you some clue. This we can think about some nitro derivatives. Okay, so just plan about some retrosynthetic analysis and write what will be the first step for retrosynthetic analysis. So we can think about this nitro group. Okay, as I given you the clue. So this nitro group If we have and we have this alpha beta unsaturated, more specifically alpha beta unsaturated nitro group, then we can easily get this. Okay, so what will be the first step? Functional group FGI. So what will be this FGI? That is reduction. Okay, so you are doing double one reaction reduction as well as this nitro reduction to get this amine. Okay, now from where we can get this compound? So as you see, it has your two functional groups, amine and this alpha beta unsaturated nitro. Okay, so from here we can get, this is also pretty much simple. Just think about some aldol type of reaction and draw the next molecule. Okay, I will give some time and think about this, the next step. So I will give you the clue nitroaldol reaction as a key step. Okay, you can draw now. So this nitroaldol reaction we can think about, right? So nitroaldol reaction basically what it will give. So if you treat this nitromethan with base, so it will generate this carbanion and it will undergo aldol reaction as you have this electrophilic aldehyde. So it will give this alpha beta unsaturated nitro group, right? So this nitromethan is commercially available, no problem. So now we have to think about this, uh, the retrosynthetic plan for this aldehyde and amine group. Okay, so what will be the next? Think. So we have this aldehyde and now this amine functional group. Okay, so what we can plan? So like two functional groups are there. So accordingly, we can have two different retrosynthetic approach. So just think and draw the right one. Like which one will be the more approachable? Okay. So now we'll play about this part. Okay, this left hand side part. Okay, so this part we need to do something. If you see, I have drawn this with a square bracket, not square bracket. So this circle I have done. So this we can think about from some reduction of type of, okay, it's a reduction. If we think reduction of cyanide, okay, we will get this extra CH2 and NH2, right? So, so this we can get. Now, what type of CC1 disconnection again we can do? Which CC1 we can disconnect, right? So we can disconnect this CC1, okay? So this, so alpha to aldehyde. So generation of alpha carbon and to aldehyde is easy. Also generation of beta positive charge next to carbon cyanide also easy, okay? So like this acrylonitrile. So where this will act as a alpha beta unsaturated carbonyl compound because of this electron withdrawing group effect of the cyanide and also this aldehyde. So alpha position we can easily generate this carbanion, right? So it will undergo Michael on for addition and it will give this product. So so we have done with this retrosynthetic approach. If you have any doubt or any question in your mind, just ask me right now or write in the comment section. No doubt. Okay, then we'll move to our forward synthesis. Okay, so I have shown you the starting materials for this two case for this retrosynthetic approach. So we can see the two starting material. Also, I have write I have I wrote the reagents for this first step. Okay, so what will be the possibility? Okay, so the reagent is sodium hydroxide. It is a base, so it will abstract some proton. Then obviously, so where is your acidic proton? Most acidic proton, and that that will abstract by the sodium hydroxide. Okay, so just find the acidic proton here. So one of the starting material, so two starting material is given. So one of the starting material is bearing some as alpha acidic proton. Now you can see easily find out. So this CH is acidic proton because it is alpha to carbonyl or aldehyde. So sodium hydroxide obviously it will abstract proton here, and what will be the next move? So after abstracting proton, it will generate the carbon anion, right? So this carbon anion here it will generate, and what will be the next move? So it will act with some electrophile. So what type of electrophiles is there in your system now? So you have this acrylonitrile or this alpha beta unsaturated cyanide compound. So here this due to this electron withdrawing group, the cyanide, so this beta carbon is it will show some partially positive character. Okay. So this carbon and beta carbon is basically electrophilic. So this carbon and will add to the beta position of this acrylonitrile and it will give some 1,4 addition product or that is called Michael addition product. So first step is 1,4 addition. Okay. on for addition. Now next step, for the next step I have written the reagents nitromethane also in triethylamine. Okay, triethylamine nitromethane is the reagent, and triethylamine is the base. Okay, so what will happen in this step? So is base, so it will abstract some acidic proton. So where is your acidic proton? So this acidic proton is in nitromethane itself. So this nitromethane, the pK value is around 9, and triethylamine pK is around 10. Okay, so it will abstract proton from this nitromethane and it will add now nucleophile. Okay, so what will happen? You have electrophile here aldehyde. Cyanide is also having, an aldehyde is also having, but electrophilicity of aldehyde is more compared to the cyanide. So what will happen? It will add to this aldehyde and it will give some nitrile or addition product. Okay. So what will be the product? You just write in your notebook. You just write the product. So basically, you will get some nitrile product, right? What is the nitrile product? Okay, so right product is, I guess, pretty much easy. You'll get some beta hydroxy nitro compound. Okay, alpha beta. Okay, beta hydroxy nitro compound. Now the next step, for the next step I have written the reagent P2O5. Okay, so what is P2O5? Phosphorus pentoxide. Okay, so what is the role of, what does this P2O5 do? Okay, what is the role of P2O5? If you know, then it's pretty easy for you to do the next reaction or to draw the next compound. Or if you don't know about the role of P2O5, I will give some hint. P2O5 phosphorus pentoxide, it is an dehydrating agent. Okay, so it is an dehydrating agent. Okay, so what will happen in the next step in presence of dehydrating agent? So it will in your compound, if you have any hydroxy group, it will undergo some dehydroxylation. Okay, so that means elimination of water will happen in presence of P2O5. Okay, because P2O5 will abstract moisture and it will give some product to you. So what it will give generally? Write down the next product. I have given all the clue. You can write easily. Yeah, it will give the eliminated product. Okay. The next reagents also I have written. So you will get the alpha beta unsaturated nitro compound. Okay, very much simple. Elimination of water will happen. So give the typical aldol product. Okay, eliminated product. So now the next step, for the next step I have written the reagent hydrogen. Hydrogen mean H2 molecular hydrogen, and this Rani nickel. Rani nickel is a catalyst. So in this surface of Rani nickel, hydrogen will absorb and it will undergo some hydrogenation kind of reaction. Okay, so if you have any substrate or functional group which will undergo reduction, so it will reduce those functional groups to give the reduced product. Okay, so what you will get in the next step, so the reduction, so basically reduction will happen in this compound. So what type of reduction will happen and what product you will get, just write down. So you have nitro, this double one and amine. So which reduction will happen? You just write it down. It's pretty much simple. So reduction of nitro also happen also along with this double bond. Okay. So this is our target molecule TM, and we have completed the forward synthesis along with the retrosynthesis. Okay. So if you have any doubt, you can ask or you can write in the comment section for this problem. Okay. So now, yeah, let's move to the next problem. Yeah, this is very famous molecule tropinone. So tropinone was first synthesized by Robinson in 1917. So if you see this molecule is having this bicyclic core, having this 3 to 1. Okay, 3 1 2 3 1 2, and this one 3 2 1 bicyclic system, bicyclic core. So how we can plan for this molecule? Okay, so we can redraw is, so we can redraw this molecule like this. Okay, so now it is, yeah, now this is very simple. Now it's looking like very simple. So what type of retrosynthetic plan we can apply for this molecule? Okay, so what will be the retrosynthetic plan for this molecule? Just think and draw in your notebook. Okay, I will show then. Okay, after you write, then I will show you. If it is drawing like this, for visualization purpose, it will be very difficult uh, to plan the retrosynthetic plan. Now I have written like this, so it is very difficult. It is very easy now. I'll give some clue. You can think about this CC1 and this CC1 disconnection approach. Okay, so now you can. It's easier for you to plan this retrosynthetic analysis. Okay, so that means this nitrogen. Okay, so this amine type of things, that will be the nucleophile. Okay, so that will be the nucleophile mean it can have the, so this carbon should bear delta positive charge. Okay, and this carbon should bear delta positive charge. Now in this molecule, if you see alpha beta unsaturated carbonyl compound we can take. So like that. Okay, so this will be our retrosynthetic analysis in first priority. Okay, so this, as I told you, so this is the one disconnection approach, and it will lead to this methylamine and this alpha beta unsaturated dicarbonyl sorry di alpha beta unsaturated carbonyl compound. Okay, cyclic compound. So any doubt in this slide you can ask. Okay, so move to the next, the retrosynthetic plan for this molecule, how we can synthesize this molecule. So this CC1 disconnection, so this is symmetric molecule now. So this CC1 and this CC1, this connection we can think. So for this part, we can easily think about this malonaldehyde, and for this part, this keto carboxylic acid. Okay. So any doubt for this purpose for this slide? No, right? So we can move to our forward synthesis now. Now in forward synthesis, we'll start from this under pyridine and heat condition. Okay, what will happen? So this will abstract proton to acidic proton. So basically, first step, this uh, this carbon carbon bond will form, and you will get this unsaturated double bond, right? Similarly, here also in this second step, you will undergo the same reaction and you will get the product. Okay, so now, so now what will happen? I have drawn the reagents methylamine. Okay, so what will happen? So it is the nucleophile, and you have your electrophile in the system. So write down the product. Then I will show the next step. Okay, this is a very simple product. You can write easily. So you'll get some one for addition product, right? So this product you will get. So now the elimination of CO2. Okay. So this is the compound. In this compound, you are having this beta carboxylic acid. Okay. Alpha, this, yeah, alpha and beta carboxylic acid. So it will, if you heat this compound, if you treat with heating condition, you will get the elimination of carbon dioxide, and you'll get this eliminated product. Okay. So this tropinone. Okay. right? So now this name reaction, okay. So this name reaction na in first step. So this the name reaction like the for this step is known as Doebner condensation reaction. Okay, so I'll write down the mechanism for this Doebner condensation. Okay, so you can see in presence of pyridine, what will happen? This enolate will form. Okay, so this enolate will form. Now this enolate will undergo this. So it will add to this aldehyde. Okay, diamannone aldehyde, and it will give this beta hydroxy carbonyl compound, right? So alpha beta hydroxy carbonyl compound. Any doubt for this step? Yeah. So the next step will be the also same. Okay. Again, enolate generation. So what will be the next then? Write down the product for the next step. So same product. Okay, you will get this beta hydroxy alcohol. Okay. So now elimination will happen. So in pyridine heat, first what will happen? So this decarboxylation will happen. Okay. So decarboxylation will happen. What will happen? This pyridine will abstract proton. Right. I have so pyridine will abstract proton. Then this OH proton will OH bond electron will fall here, and this bond will break, and we will get end up with this hydroxy elimination product. Okay, and you will get this similar way in the next step also you will get the same product. Okay, like same elimination product. So next for this this step you can draw the mechanism. Just I will give couple of minutes and you can draw the mechanism. Also, if you have by that time, if you have any doubt, you can ask. Okay, so I guess all of you have drawn the correct mechanism, and if you have any doubt, you just ask me. So this Doebner condensation reaction is very important. So it is utilized in many of the total synthesis. Okay, if it is done, then we can move to the next problem. So this is the molecule for our next target, TGT or TM. Okay. So this is our TGT or TM. So this molecule you can think so 6 5 spirocyclic molecule with having cyclic amide, that means lactam, beta lact gamma lactam, also this 6 member carbonyl compound. So these are the functional groups it is having. So just plan the correct retrosynthetic approach for this molecule. Just thing in mind, or you can draw to get a fast forward, fast retrosynthetic compound. So what will be the first? So you can have some functional group addition. Okay, so we can add some functional group in our first retrosynthetic arrow. Like we are adding this ester. Okay, we are adding this functional group ester. So for what purpose we are adding? Okay, so now the next move, what will be the next move? So you now we are adding this functional group. So for what purpose we are adding? If you think that purpose, then we can you can write down the next retrosynthetic structure. Okay, just think and write. So what will be the next move? So this is the condensation reaction. Okay, so Claisen condensation reaction. So you'll get this two ester. Okay. So what is the next then? Next will be the lactam formation ring. Okay. So this CN bond disconnection approach is the next step. Okay. So this will be the next target molecule. Now you can think about the retrogenetic plan for this molecule. Okay. So some functional group interconversion also you can think. I have given you the hint that some functional group interconversion we can think about for the next move and write. Yeah, we can think about some this nitro group. Okay, so this is the functional group interconversion. So this amine from nitro. Okay, we can think some reduction we can do. So now from where we can get this molecule? Okay, so this is now very pretty symmetrical molecule. If you clearly visualize this molecule, so you'll see some you'll see some connectivity or idea what to do, okay, with the next step. So this is very symmetrical molecule. If you see, this is having this ester fragment, here ester fragment, two carbon chain ester fragment, here also two carbon chain ester fragment, okay. So we can think about this CC1, this CC1 and this CC1 disconnection, okay. So we can think about this nitromethane and three equivalent of this alpha beta unsaturated carbonyl is like ester, okay. So what is the next? So next is like this, okay. So you can have this nitromethane, so it can act as a beta carbon here, beta carbon here, also beta carbon here, okay. So this is very much gettable, I guess. Or if you have any doubt, you can ask or in write in comment section. Yeah. So we'll move to the forward synthesis. So for forward synthesis, I have written down the reagents, the starting material, also this three equivalent of this compound, okay. So dbu 5 mole percent, so this is catalytic reaction, it will abstract proton from nitromethane. And what it will do, what it will do, you are having three equivalent of this methyl acrylate. So that what what is the use of this three equivalent of this methyl acrylate, I have already discussed. So just draw the next steps, okay. So like three equivalent of utilizing this three equivalent of this electrophilic reagent, you just draw how it will be the next step, okay. So already in next slide we discussed, so dbu will abstract proton from here nitromethane, and it will undergo 1,4 addition or Michael addition with three of these methyl acrylates, okay, and it will give this big molecule, okay, right. So you will get this molecule, okay. So this nitro compound. Now the next, for the next step, I have written the reagents, that is some reducing agent hydrogen with ranny nickel, okay. So what it will do, so it will reduce your substrate. You just find what type of functional group presents in your substrate which can undergo or which may undergo reduction, okay. So the nitro group is there. It is purely obvious that nitro reduction will happen, and you will see this amine, okay. So now the next step, for the next step I have written the reagents, okay. So what will happen, so you just see we are having this sodium hydride in catalytic amount of methanol, okay, some acidic source. So what reaction will happen? So what sodium hydride will do? So it will do some two conversion will happen. Okay, two reaction will happen in the same step. Just see what will happen. Just think and see. Yeah. So first step is Claisen condensation will happen, and what will be the next? Next, if you see in your molecule, amine is also there. So it will undergo. It will take proton from this amine NH, and it will go some lactam formation reaction. Okay. So it will go Claisen condensation reaction in the upper half, and from the bottom half it will give some lactam. Okay, so basically you will get this product. Okay, now what will be the next is also very much easy. So sodium hydroxide, aqueous sodium hydroxide, and HCl is there. Okay, so what you will get, what sodium aqueous sodium hydroxide will do, basically some hydrolysis will happen. Okay, hydrolysis of lactam or ester. So lactam is more stable than ester. So instead of hydrolysis of ester will happen, and then we are treating with HCl. So just see what you will get. So just think and write down the product. It is very much easy. First step I already given you the clue. Ester hydrolysis will happen. So you'll get some compound that is acid, and then in HCl, what you will get. Also, if you remember the target molecule for this problem, you can easily get the product. So, did you write? So basically, first step is carboxylic acid will form. Then, if you treat with HCl, it will undergo decarboxylation. Okay, and it will lead the elimination of this whole group. So you will get this product. Okay, so this is our target molecule. That's why I told you that if you remember the structure of target molecule, you can easily write down the structure. Okay, so this is very much interesting example. And if you have any doubt for this problem and retrosynthetic approach, you just ask me freely, and also you can write in comment box. Okay. Yeah, so if no problem, then we can discuss the next problem. Okay, so this is our molecule, next molecule. So what type of functional groups are there? So it is also in pyrocyclic compound. Also, it is having ester like beta keto ester and olefin in the six member ring, right? So what will be the next move? First move, okay. So we can think about this CC1 disconnection, okay. So this CC1 disconnection will lead to this synton, okay. So this side is donor synton, this side is as acceptor synton, okay. So what will be the synthetic equivalent for this synton, okay? Just write down the synthetic equivalent or think in mind, then I'll show you. Yeah, so this will be the synthetic equivalent, okay. Again, same reaction, okay. Collision condensation we have to do like our previous example, okay. We did the same reaction. So now what will be the next, okay? So like this CC, sorry, yeah, this CC1 disconnection approach will leads to these syntons, okay, donor synton and acceptor synton, right? So what will be the synthetic equivalent? So this for donor synthon, this is the synthetic equivalent, and for acceptor synthon, this halide must need. So this is the electrophile. So you need this synthetic equivalent. Okay. So for forward synthesis, so if you have any doubt, just ask me in this slide. Then I'll go to forward synthesis. Yeah. So we can move to forward synthesis. So we'll start from this ester. Okay, ester derivative. So we need some. We need to do some electrophilic uh, like inolate chemistry and then treating with this inolate with electrophile. So that electrophile is, so first what will happen, LDA, it will abstract this acidic proton. Also this allylic proton is acidic next to ester, alpha to ester also acidic. So it will abstract this acidic proton. So LDA basically abstract this acidic proton, right? And it will give generate this enolate. Now the next is you are treating with this bromo derivative. So it will undergo, yeah, it will undergo this substitution reaction. So what you will get, so what will be the product? Just write it down. Then I will show you. Yeah. So this will be our product. Okay. So next step is similar condition. Clayton, yeah, Dickman condensation reaction. So Clayton, yeah, I forgot the name. Dickman condensation. I'm sorry. So this will be the Dickman condensation. So in sodium hydride and THF. So what will happen? So this enolate will form here, and it will undergo addition to this, and it will give this product, right? Beta keto ester. Any doubt? I guess no doubt. This is very pretty simple. So this is our target molecule, right? So what will be the next target molecule? Okay. So this bicyclic compound, okay, 221, 221 bicyclic compound. And this is our next target molecule. What type of retrosynthetic plan we can think? Just draw. Yeah, what we can plan here? We can plan some, yeah, functional group interconversion. We can plan in the late stage some Diels-Celder reaction also. So like this amine to nitro. So this will be the functional also another functional group interconversion, that is reduction, and this amine to this secondary amine, primary amine to secondary amine, this will be done by reductive amination. Okay, and this double one we can reduce here. Now from where we can get, so if you see this is in 6 2 to 1 bicyclic molecule. So so we can plan about, I'll give you some clue. We can plan through Diels-Celder reaction. Okay, we can plan to get this molecule. So this thing about Diels-Celder reaction, so Diels-Celder reaction basically it will give 6 member ring, okay, not 5 member ring. So what type of diene and dienophile you have to take? Just think about Diels-Celder reaction and draw the next structure. Okay. So what will be the next structure? Write it down, then you'll find easily. Did you get? So I'll give you this CC1 disconnection approach. Okay, that is one of the clue. Now you can easily find the diene and dienophile. Yeah. So this part we can have this diene. This part you can have your dienophile. Okay. So this is diene and this is dienophile. Basically, this is cyclopentadiene. This is CP or cyclopentadiene, and this is the dienophile. Okay. So for forward synthesis, we should start with this. Yeah. For first, we'll make this dienophile. Okay. We'll make this dienophile, and then we'll carry out this Diels-Alder reaction. So DBU, then this what will happen? Basically, it will take proton here and it will undergo aldol reaction, and it will give this alpha beta unsaturated nitro compound, that is your dienophile, right? So now you need to treat with diene. So what will be the diene here? Diene is cyclopentadiene. Okay, cyclopentadiene. So basically you will get this Diels-Alder attack. Okay, so this CC1 and this CC1 formation will happen, and you will get this Diels-Alder attack. Now, so next is you have to reduce this nitro group. Okay, so under reducing nitro as well as this double bond. Okay, so under a hydrogen palladium circle condition, this hydrogenation condition will give the reduced product both double bond and nitro reduction product to keep this amine. Okay, any doubt? So the next step is to install this, convert this primary amine to secondary amine. Okay, so you can easily treat with some aldehyde, nitromethane, sorry, aldehyde like ethanaldehyde, and some reductive amination kind of thing to get this product. Okay, so you get easily this product, secondary amine. Okay, so this is our target molecule, and we easily get this is achieve this molecule from this via this cellular reaction. Okay, I guess if you have any doubt, I guess this is pretty much easy example. By cellular reaction, you can get your digit target molecule. Okay, so if you have any doubt in this slide, you can ask me, or also we will stop here today and we'll discuss the next problem in the next week. Okay, so till then, do well. Best of luck. So thank you for your attention. So we'll stop today and we'll discuss on the next week. Okay. Thank you.